0317 Universal Time, the Deep Space Network in Canberra registered a positional discrepancy in the trajectory of Object 3I Atlas, the third confirmed interstellar visitor ever recorded. For nearly 4 months, its orbit had been projected with millimeter precision, synchronized across NASA's Jet Propulsion Laboratory, the European Space Agency's Near-Earth Object Coordination Center, and Japan's Subaru Observatory in Hawaii. The models agreed. Atlas would complete its hyperbolic pass around the Sun and exit the inner system by early December, its speed and path locked by known celestial mechanics. That consensus no longer exists. The first anomaly appeared as a minor inconsistency, a deviation of 0.002 astronomical units in range, small enough to be dismissed as measurement noise. But within hours, sequential data from Goldstone and Madrid confirmed the same offset, growing steadily in magnitude. In the language of mission control, the solution had diverged. Every orbital recalibration introduced new residuals, indicating that the object's movement could no longer be explained purely by gravitational influence. The algorithms built to predict natural trajectories began to fail. For context, 3I Atlas has been monitored using a global network of optical telescopes, radar pings, and solar coronagraph imaging arrays. Its speed, luminosity, and spectral output have been measured thousands of times since discovery on July 1, 2025. The orbit was initially categorized as hyperbolic, inbound from interstellar space at 55 kilometers per second, passing within 1.36 astronomical units of the Sun. Its reflective signature placed its diameter near 5 kilometers, making it one of the largest known interstellar objects ever observed. These parameters were validated repeatedly, cross-checked through NASA's Horizons database and ESA's optical tracking systems. Yet as of this week, the validation loop has broken. Telemetry that once aligned across multiple observatories now produces mismatched coordinates separated by tens of thousands of kilometers. The deviation persists across optical, radar, and radio datasets, independent systems that rarely fail in unison. Attempts to reconcile the trajectory through outgassing, solar pressure, or magnetic interference have yielded no consistent model. Even the fallback simulation, run on the highest fidelity at JPL, ends with a non-convergent solution. The path cannot be mathematically closed. At present, 3I Atlas occupies a region of space where every predictive framework fails. Its motion is measurable, its cause is not. The anomaly itself is deceptively simple. 3I Atlas is no longer where celestial mechanics says it should be. Orbital solutions generated before perihelion predicted a steady, hyperbolic escape from the inner solar system with a residual uncertainty of less than 1 arcsecond, an accuracy routinely achieved for comets, asteroids, and spacecraft alike. Yet current positional data show a continuous lag along its expected vector, a gradual deceleration inconsistent with any known natural process. The displacement, initially measured at a few thousand kilometers, has now widened to nearly 40,000, a magnitude that cannot be explained by gravitational perturbations alone. Under ordinary conditions, such deviations are easily traced to outgassing, jets of sublimating material that act as natural thrusters, pushing comets slightly off course. But this explanation falters when applied to Atlas. Its composition, established through spectroscopy, is exceptionally dry, containing only 4% water ice by mass. Moreover, its coma emission profile has remained stable since August, showing no bursts of vapor or asymmetric dust structures that could produce measurable thrust. The absence of visible activity undermines the primary natural mechanism for orbital drift. A second theory, advanced by teams at the University of Bern and Caltech, attributes the anomaly to pressure from the solar wind interacting with metallic compounds within the object's surface. The hypothesis assumes an unusually high reflectivity and low density, a configuration similar to ultra-thin solar sail materials. Yet this requires an area-to-mass ratio, several orders of magnitude greater than that inferred from Atlas's brightness, implying a structure far lighter or more hollow than its estimated 33 billion tons suggest. Without a confirmed shape model, this remains speculation anchored in mathematical necessity rather than observation. A third interpretation proposes a temporary gravitational assist from an unaccounted fragment or companion body. Some radar returns have shown secondary echoes near the object's path, though none persistent enough to confirm a secondary mass. If real, such a fragment could alter Atlas's momentum subtly but significantly. If illusory, the echoes might point to instrumental interference rather than physics. Each hypothesis accounts for part of the data and fails under another. What remains certain is that the deviation is real, consistent, and increasing. The object's brightness, rotation, and energy output show no visible instability, yet its path diverges as if subject to a faint but deliberate impulse. For now, the community remains suspended between possibilities, mechanical, chemical, or something not yet defined, awaiting new measurements to decide which law of motion has quietly changed. For observers across the network, the passage of time has become the primary instrument. Every hour since the first deviation was recorded is now measured against the slow drift of Atlas across the inner system. The anomaly does not announce itself in flashes or bursts. It unfolds in precision, small corrections that no longer align, residuals that grow with each recalculation. The Deep Space Network monitors transmit updated coordinates every 6 minutes, yet each transmission arrives slightly more displaced than the last. The rhythm of observation has become a kind of countdown, steady, mechanical, and quietly unnerving. In the first week after perihelion, the object's path still appeared reconcilable. Analysts expected post-solar radiation pressure to account for most discrepancies, and there was confidence that the models would tighten once the full light curve was processed. But the longer Atlas remained visible, the less predictable it became. By the second week, optical measurements from Chile and radar echoes from Canberra began to diverge. The signals were not chaotic. They were coherent, but in the wrong place. It was motion that made sense internally, not externally. As one astronomer described it, the data felt self-consistent in isolation, impossible in context. Now, as Earth continues its orbit, the geometry of visibility begins to close. Within days, Atlas will slip again into solar conjunction, hidden behind the glare, where no telescope can safely track it. This gap, roughly 3 weeks of observational blindness, has turned into a point of collective tension across agencies. Every parameter that defines the object's behavior must be measured before it vanishes. The last confirmed vector must hold until it reemerges. If the path shifts further during that blackout, there will be no way to reconstruct what occurred in the interim. The scale of the problem is almost beyond comprehension. A body several kilometers wide, traveling at more than 50 kilometers per second, now represents a prediction error, measurable in tens of thousands of kilometers. At such velocity, even a fractional acceleration sustained over hours would rewrite its entire post-solar trajectory. The teams are racing to complete spectral mapping before the object crosses the solar limb. The light from its coma is fading into background noise. Instruments recalibrate again, searching for one more usable signal. And as the final data packets arrive, the countdown compresses into silence. In a matter of days, Atlas will pass beyond direct observation once more. When it reappears, its position alone will tell the story, whether the laws that govern it still hold, or whether something somewhere in that unobserved interval has changed the course of its motion. In the days following the disappearance of 3I Atlas from direct observation, communication between agencies began to slow. Status updates that had once circulated hourly now arrived at irregular intervals, sometimes a full day apart. Official channels cited data verification protocols and cross-instrument calibration, but the tone of the releases had changed. Each bulletin grew shorter, more procedural, stripped of interpretation. Where early reports had carried context and confidence, the new language carried only timestamps and coordinates, the syntax of containment. At the Jet Propulsion Laboratory, telemetry analysts continued to receive faint signal echoes relayed from the Deep Space Network. Most were routine background noise, yet a fraction of them matched the narrowband frequency last used to track Atlas before conjunction. The signals were irregular, almost too weak to classify. ESA teams using independent receivers claimed no detection at all. When datasets were exchanged, the inconsistencies deepened. One observatory reported a faint return from a position slightly above the predicted plane. Another placed it well below. Both could not be correct. For the first time, the problem was not with the object, it was with the observation itself. Internally, a decision was made to suspend public updates until correlation could be established. No further orbital elements were released to the Horizons database. External research institutions found their access frozen mid-query. The silence became its own data point, evidence that something significant and possibly unverified was under review. Independent astronomers began to publish partial reconstructions, most of which contradicted one another. The disagreement spread quietly through the scientific community, not a debate about theory, but about what had actually been seen. Then, on the fifth day of blackout, the European Solar Observatory recorded an unscheduled image sequence while calibrating for coronal mass ejections. In one frame, a faint point appeared near the solar limb, brighter than background noise, positioned several arc minutes from where Atlas was last projected. Over the next hour, subsequent frames showed motion, not retreating, not outbound, but curving. The data packet reached JPL 3 hours later. A review confirmed it. 3I Atlas was no longer following an escape trajectory. Its velocity vector had shifted by a measurable degree, placing it in a decelerating arc within the inner system. No outgassing, no fragmentation, no visible debris. Only a course correction that no natural force could produce. And after that confirmation, the official report stopped. In the weeks that followed the last verified sighting, the narrative surrounding 3I Atlas divided into two distinct registers, what could be proven and what could only be inferred. The verified record remained small, concise, and irrefutable. An object of interstellar origin entered the solar system on a hyperbolic path, exhibited measurable non-gravitational deviation after perihelion, and failed to conform to any predictive model built upon natural mechanics. Its final confirmed position showed deceleration inconsistent with solar or planetary influence. Beyond that, the data ends. What persists is interpretation. Some teams continue to treat the anomaly as a result of unknown material dynamics, perhaps an exotic, low-density structure responding to solar radiation in ways not yet characterized. Others argue for a mechanical explanation rooted in active processes, internal or external, that no natural framework can reproduce. Neither perspective can claim completeness. The available data is too narrow, the observational gap too long. Every attempt to resolve the event through conventional analysis has led to another layer of uncertainty. The institutional response has grown equally measured. NASA, ESA, and JAXA have all shifted Atlas from active tracking to passive surveillance, awaiting its next reappearance along the projected corridor beyond Mars' orbit. There are no missions proposed, no press briefings, only scheduled observation windows, the slow rhythm of science resuming. After an interruption, it still cannot define. Quietly, instrument upgrades are being accelerated. New sensors are being recalibrated to detect motion with greater precision, as if preparing for a future encounter with the same question. For those who observed Atlas from the beginning, the object now functions less as a mystery to be solved than as a mirror to our limits. Its behavior did not violate physics. It only expanded the region where physics must be rewritten. The anomaly stands as a reminder that certainty in astronomy is never final, only provisional, that space itself retains the capacity to act beyond expectation and without warning. The next detection, whenever it comes, will decide whether 3I Atlas is simply the most unusual natural traveler ever recorded or the first indication of a design that predates our understanding. Until then, all that exists is the record, numbers, images, silence. And somewhere within that silence, an object continues its course, unchanged, unclassified, and waiting to be seen again.